In the next part of the notes, we're going to discuss something called the intermediate value theorem. This, we're going to abbreviate. We're going to call it the IVT. And it's what we would call an existence theorem. And in calculus, by the time we're done at the end of the year, we'll have what I would call 3 existence theorems, which basically means it's a theorem that guarantees the existence of some number in an interval that meets a certain condition. So a clue to when you're going to use an existence theorem is when the problem says, show there's at least one number such that, or show that there exists a number such that. That's going to trigger your brain to the fact that you're using an existence theorem. And the other two won't come about for us for a couple months. So this is the first one that you have that I would call an existence theorem. And it's very, very common sense out of the math realm. So I'm going to not talk about it in terms of f of a's and b's and k's and all this stuff in here. I will in a minute. But the theory behind it is very simple. It just says this. Let's talk about, say, temperature. If it was 20 degrees this morning, and when you go home from school, it's 37 degrees, and temperature is a continuous function, which means it just doesn't hop from 20 degrees to 27 degrees. Even if it goes quickly, it still passes through all the other temperatures on the way up. So what the intermediate value theorem says is that for any temperature in between these two, there had been a time today where it was 28 degrees. Kind of makes sense. Or if you're driving a car and speed is a continuous function. For example, you don't just jump from 30 miles per hour to 50 miles per hour. You go through all the other speeds along the way. So what this says is if you're driving and you were going 30 miles per hour and then you were going 50 miles per hour, it just says at some time you had to have been going 40. You could have been doing it more than once, just like with the temperature today. It might have been 28 degrees more than once, but it had to have at least hit that one time. So now let's take it and put it on all of its math splendor here. So this is what I would call the hypothesis of the theorem. So this only works if a function's continuous, so you should block that in. And so I won't lift my pencil when oh my gosh, this happens every time. I am so sorry. So I'm going to go to an A here and a B here. And this means the interval's closed, so I'm going to have solid dots. I also have their y values, their f ofs, not equal to each other. Basically what that means is I don't have a horizontal line. I am going to put f of A here and say f of B. So A comma f of A, B comma f of B, and what I will do is I will head on over from A to B and not lift my pencil. So perhaps I'll just go like this. All right? Now, what the intermediate value theorem says is if I have any number between these y values, which means any dot in here, I'm going to put it right there. I'm going to call it k, and I could have gone anywhere. There's at least some number in this interval so that f of c equals k. At least one. Could be more than one. So there's mine right there. I had to have hit that graph somewhere if I continuously went from one end to the other. So a couple things to note. There can be more than one c. Well, that should make sense because I could have, I can go like this. And if my k is here, I've got 1, 2, 3, 4 times I've hit it. Same like I said with temperature. Yeah, if it goes from 27 degrees now to supper time, 58 degrees, it could have been 40 degrees a couple times during the day, but this theorem guarantees that it had to have happened at least once. Also, the function must be continuous because if it's not, this doesn't happen. If there's like a break in the graph between the two, then you'll notice I have no, sorry, excuse me. I've got such a bad cold, but the function has to be continuous. Even, let's just draw a really basic, not continuous function, one with the hole in it right here. So if I say my k is right here, there really isn't a c that matches. So you do have to make sure it's continuous. And the last part is, what is it used for? Why would we even need to have this in mathematics? Generally, what it's used most for is for guaranteeing, I'm not sure how to spell that, guaranteeing the existence, again, this is why we call it an existence theorem, guaranteeing the existence of zeros is really what it's used the most for. So what I'm going to do is go show you how we use it. So let's go to this. So we've got a cubic function. We kind of know what the graph of those looks like. We're not going to go graph it. But I am to show that there is a zero. So I'm trying to show that there exists some number. All right? So let's go take a look at what we do. First thing we're going to do is say, well, what happens when x is 2? And I'm going to go do f of 2. So basically I've got my a and my f of a is what I'm calculating. And when I put a 2 into that function, I get a 5 out. And then I'm going to do my b, which is 1, and my f of b, which would be f of 1. So basically I've got 2 points. I've got the point 2, comma, f of 2, and I've got the point 1, comma, and when I put a 1 in there, I get a negative 1. So even if you picture this graphically, because sometimes the visuals are the best, I've got some function, a cubic one, that sails through the point 2, 5, and also through the point 1, negative 1. Well, if it's continuous, which all polynomial functions are, I can guarantee the existence of at least one zero, because zero's between negative 1 and 5, so it's got to hit it at least once. Well, how do you write this? And this is the most important thing I'm going to tell you. When you have to explain yourself on free response questions, you have to make sure that the hypothesis is met, and then you have to draw the correct conclusion. So this is what I mean. I mean, the concept, again, calculus is easy. I mean, obviously, I had to have passed through 0 if I go from 5 to negative 1. Common sense. If I'm going from 5 down to negative 1 and I never miss my pencil, I better hit 0 at least once. However, you can't just say it's common sense. First of all, you have to say that this function was continuous. So you would say x cubed, let's even just do this, f of x is continuous. All polynomial functions are. So f of x is continuous. You don't have to write because all polynomial functions are. You just need to state that you're aware of the hypothesis and you're aware that it was met. All right? So f of x is continuous, and since f of 2 equals 5 and f of 1 equals negative 1, then you have to state the theorem you're using. So we'd say the intermediate value theorem, you have to state that or you get points off if it's a free response, guarantees all right, so we've got f is continuous since f, and, I should have put it and. F of x is continuous, and since f of 2 equals 5, and f of 1 gives me negative 1, the intermediate value theorem guarantees a, you could call it c, or a number, all right, between 2 and 1, such that f of c would have to equal 0. And again, you can word it differently than that, but you do have to state that the hypothesis was met, that you had a continuous function. You do have to state that you've evaluated that function at both points, and you do have to say that the intermediate value theorem is what guarantees a number in between them. Really, though, all you're trying to tell me with all this math gobbledygook is that when you go from 5 to negative 1 and you don't pick up your pencil, you pass through 0. For piecewise functions to be continuous, they must seal at their endpoints. If not, there's going to be a gap. It should make sense to you that if I have a piecewise function and one piece goes like this to the right of 2 and the other one ends up going like this to the left of 2, I don't have a continuous function. So algebraically, what you have to do to make them continuous is you're going to have to make sure that these meet at that boundary. So a typical type of question, and I starred this because this is on every multiple choice practice test I've ever seen, is that they'll have you find a value, or even one or two, sometimes there's a missing A and a B, that will force the function to be continuous. So I've got a piecewise function, I've got a cubic piece, and I've got a linear piece. I have to force them to seal up at 1, so that wherever the cubic part was, at 1, it goes seamlessly into the next piece of the graph. So what you're going to do is, you set them equal at that barrier, at that boundary. So you're going to put a 1 in for x in the cubic function, and you're going to say, well, 3 times 1 cubed. You're going to say that has to have the same output as the other one does at x, because again, if not, if they spit out different answers, I'm going to have a split in the graph. So that y value on that boundary has got to be the same to force them to seal up. So you basically just stuff it in, and you say, well then, a times 1 plus 5. And you just evaluate it. So on the right I have 3, and on the left I'm going to have a plus 5. So the question is, well then what's a? A would equal -2. So in order for my line to seal up perfectly and make a continuous function, its slope would have to be -2. Or you will just be in search of that missing a. So that's the end of the video notes. I told you about 10 minutes. I guess it's about 11, but no worries. And you could actually keep working in your homework if you would like to. If you're kind of cruising on the 1-4, I believe this can get you up to about numbers. Boy, you could get close to the end. I only have a little bit more to tell you tomorrow. So you guys have a great day.